So notice they want us to identify the first four non-zero terms of this particular Maclaurin series by making appropriate trig identities, properties of logs. So not only can you use substitution or you can use multiplication, you may have to do some trig identity substitutions in order to develop the Maclaurin series. So first of all, let's take a look at cosine squared x. Well, we know what the Maclaurin series for cosine of x is. The issue is you've got a cosine squared here. So we do have a double angle formula that would get us down to a cosine function to the first power. Using a Pythagorean identity substitution wouldn't help us, because even if I tried to do a Pythagorean identity substitution, I'd still be stuck with a 1 minus sine squared. The issue is I want to get it down to a cosine to the first power. So I've got that double angle formula for cosine squared. So if you remember, cosine squared x by your double angle formula is equal to 1 plus cosine of 2x, all divided by 2. And remember, if you know the cosine double angle formula, you know the sine double angle, because remember, what's the only difference between the sine and the cosine? The sine will have a subtraction sign in it. Okay, so remember the sine squared of x is 1 minus cosine of 2x all over 2. All right, so now another way I could write this particular formula is writing it as 1/2 times 1 plus cosine of 2x. So that's another way I could express the double angle formula for cosine. Okay? So now what I'm going to do then is I'm going to use this double angle formula to create my Maclaurin series for cosine squared x. So then cosine squared x, Maclaurin, remember I'm only generating out to the first four terms, is going to be the 1/2 times, I'm going to open up a big set of brackets because everything's going to be multiplied by 1/2. 1 plus. Now remember, I know what the Maclaurin series for cosine of x is. So remember, the Maclaurin series for plain old cosine of x is going to be equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. So there's this 1/2 times a quantity of 1. So that takes care of this part of my double angle formula as well as the 1. Now what I want to do is I want to generate my Maclaurin for cosine of 2x. So what I'm going to do is just substitute, take out my x and replace it with a 2x. Now don't confuse yourself. I still have to start this Maclaurin for cosine of x with 1. So it's going to be plus 1 minus the quantity of 2x to the 2nd power over 2 factorial plus 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial. So any questions on how I did the substitution into that cosine double angle formula? So now remember, it wants the first four terms. So you want to make sure if you have any like terms that you go ahead and you combine them. So inside my brackets, I can go ahead and I can add 1 plus 1 together, which will give me a 2. So that counts as one term. Minus the quantity of 2x to the 2nd over 2 factorial plus the quantity of 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial. So there I have my 1, 2, 3, 4 terms. So there's my Maclaurin series for cosine squared x. All right, so any questions? So you can use those trig identities. You can use your trig identities to also manipulate to come up with a Maclaurin series. So any questions on that particular example? Again, make sure you're always reading the directions. Make sure your answer has the number of terms it's asking for. So that 1 plus 1 is not considered 2 terms because they are like terms. All right, any questions on that? So now you can also use your properties of logarithms to develop your Maclaurin series as well. So I want to develop a Maclaurin series for the natural log of 1 minus x divided by 1 plus x. So now remember, what's your quotient property of logarithms? How can you separate this? You can separate this into what? Subtraction. So I can rewrite this as a natural log of 1 minus x minus the natural log of 1 plus x. Now, I had you on the back of your, on the green sheet we did the other day, remember we did write out what the Maclaurin series for the natural log of 1 plus x is. So remember, the Maclaurin series for the natural log of 1 plus x is your x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4. Now, when you're doing these Maclaurins, sometimes it's a good idea to take it out an extra term or two besides what the directions are asking you for. Because sometimes when you go to do these combination with subtraction, you're going to find terms start canceling out. So you're going to have to generate and tack on extra terms. So what I always do is I always start by taking it out an extra 2 terms or so. All right? Because I see that subtraction side, and I know I'm going to start having to combine like terms. I very well may get some terms to cancel out. All right? So now, if I know my Maclaurin series for natural log of 1 plus x, I can generate my Maclaurin series for natural log of 1 minus x by simply doing what? By plugging in a negative x into this series for x. So the natural log of 1 minus x is going to be equal to the negative x minus negative x squared, that 2 should be on the outside, over 2, plus negative x to the third over 3, minus negative x to the fourth over 4, plus negative x to the fifth over 5, minus negative x to the sixth over 6. And when I simplify that, that's going to give me a negative x. When I square negative x, that's going to be a positive, so that's going to be, I'm still going to have a minus x squared over 2. This is going to be a minus x to the third over 3, minus x to the fourth over 4, minus x to the fifth over 5, minus x to the sixth over 6. So this is what your natural log of 1 minus x is. So any questions on how I have generated the Maclaurin series for the natural log of 1 plus x and the natural log of 1 minus x? So now remember what I want to do by using my properties of logarithms. I want to take the Maclaurin series that I generated for natural log of 1 minus x and subtract it from the Maclaurin series for natural log of 1 plus x. Watch your order here. So again, I'm just going to write the natural log of 1 minus x is my negative x minus x squared over 2 minus x to the third over 3 minus x to the 4 over 4 minus x to the 5 over 5 minus x to the 6 over 6. I'm subtracting it from the Maclaurin series natural log of 1 plus x, which is x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4 plus x to the fifth over 5 minus x to the sixth over 6. Again, we may have extra terms in here, but again, you have to have at least 4 terms in your final answer. All right, so any questions on the operation? So now it's a matter of combining your like terms. So now I'm looking for anything that has an x in it. So here's my negative x. Here's another x to the first. So those are like terms that I can combine. So I have a negative x minus x. So negative x minus x is going to give me a what? Negative 2x. Next, I've got an x squared. So I've got a negative x squared here, as well as a negative x squared here. So when I go to subtract negative x squared over 2 minus negative x squared over 2, what's going to happen with those terms? Cancel out. That's why I said it's a good idea in the beginning when you're having to manipulate these with operations, start in the beginning tacking on an extra term or two so you don't have to go back to the original Maclaurin series and figure out more terms. So next I have a negative x to the third over 3 minus an x to the third over 3. So I can combine them, and that's going to give me a minus 2x to the third over 3. And what happens with your minus x to the fourth over 4 minus a negative x to the fourth over 4? What's going to happen with those? Those are also going to do what? Cancel out. So I have a negative x to the 5th over 5 minus x to the 5th over 5, which is a negative 2x to the 5th over 5. The negative x to the 6th over 6 minus negative x to the 6th over 6, that's going to cancel. Do I have enough terms? No. What are the directions asking me for? They're asking me for 4. So what's this next term going to be? Negative 2x to the 7th over 7. So any questions on how you can use your properties of logarithms as well to help you generate other Maclaurin series? All right. Now imagine how long and nasty this problem would be if you did not have memorized what the Maclaurin series for natural log of 1 plus x is. You would have to generate by hand the Maclaurin series for natural log of 1 plus x, generate by hand the natural log of 1 minus x, and then actually subtract those. So like I said, that's what the advantage of having those Maclaurin series on that green sheet memorized. This problem is a lot quicker if you know it because, again, these are your basics that you can then manipulate. All right, any questions on those? All right, let's take a look at, besides, we've seen where we can subtract Maclaurin series. We've seen where we can multiply. Here is another case where we're actually going to multiply two whole Maclaurin series together. So here's my e to the x times cosine x. So again, we know what the Maclaurin series for e to the x looks like. Again, looking on your green sheet, remember you've got the 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial. Again, all I need is the first 4 non-zero terms. I'm going to take it out one more in case I need it. I also know what the Maclaurin series for cosine of x is going to be. So cosine of x, remember, is my 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. So now I want to find the product of these two Maclaurin series. So e to the x, cosine of x is going to be equal to, some of you may find writing the product vertically is helpful. Some of you may find writing the product horizontally is more beneficial to you. It's kind of an eeny, meeny, miny, mo, whichever you want to do. But again, you are going to have to multiply 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial times 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And I just thought of something I've never tried with this. I don't know, when you guys multiply, when you guys were taught multiplying like trinomials and trinomials together, how many of you have ever seen that box method? I've never tried it with the Maclaurin, but I bet you that may be another way you could also visually multiply these together if you find that that's more helpful to you. All right? But you are going to have to use your distributive property. All right? So I'm sorry to say there is no easy way around this. Remember, we're only generating it to the first 4 non-zero terms. All right? So the first term here is I'm going to distribute as a 1. So I'm going to distribute my 1. So that's going to leave me with a 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. So that comes from multiplying the 1. Ouch. Plus. Now, next one is going to be x times 1, which is x. The next one's going to be x times x squared over 2 factorial. So what is x times x squared over 2 factorial going to be? X to the 3rd over 2 factorial. The next one will be x to the 5th over 4 factorial. Then I'll have a minus x to the 7th over 6 factorial. Now, kind of keep an idea. Yeah, Brian?
X to the 3rd, should I be negative?
Yes, thank you. Thank you. Oh, all that work and I would have dropped the negative sign? Oh, good, 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 good. Yeah, I'm going to circle that to make sure I don't forget that that's negative. Now, keep an idea. Notice what I've generated so far. I've generated a 1, a constant. I've generated an x squared. I've generated an x to the third. I've generated an x to the fourth. So we know that at this point, unless something else happens, the highest exponent, because I only need the first 4 non-zero terms, as long as nothing cancels, I'm only going to have to take this out to the x to the fourth. So when I look at my next term, I'm going to distribute x squared over 2 factorial. I don't necessarily have to multiply it all the way through to get like an x to the 8th or an x to the 10th. So for example, when I distribute this x squared over 2 factorial, that's going to give me 1 times x squared over 2 factorial. So I have that x squared over 2 factorial. And then I have an x squared over 2 factorial times an x squared over 2 factorial, which is going to give me a minus x to the fourth over, don't multiply out the factorials, you can leave it as 2 factorial over 2 factorial. And then this is going to give me a plus x to the 6th over 2 factorial times 4 factorial. And then a minus x to the 8th over 2 factorial, 6 factorial. So now my next term is going to be the x to the third over 3 factorial. So I just needed to worry about distributing it x to the third over 3 factorial. Do I really need to worry about taking it out any larger than that x to the fourth power? No. So, but don't forget, you do have this last and final x to the fourth over 4 factorial that you do have to multiply by 1. So that would give me a plus x to the fourth over 4 factorial. Just to save myself some time, I'm just not going to distribute that x to the third over 3 factorial out to x to the fifth, out to x to the 7th, or out to x to the 9th. You can if you really want to. All right, but remember, the question's only asking me for the first 4 non-zero terms. All right? So now let's start combining like terms. I'm starting with my constant. Are there any other constants that I generated that don't have an x in it? No. So I'm going to start with 1. I've got x squares. So identify all your terms that have an x squared. I have an x squared here. I've got an x squared here. I think I got them all, don't I? Now, when you're doing these, you don't have to worry about actually getting common denominators and combining them into one fraction. Group just your like terms together. So I'm going to take 1, add it to negative x squared over 2 factorial plus x squared over 2 factorial. But I got a problem, don't I? What happens with those? They cancel out. They cancel out. So I can't include that as one of my first 4 terms. So I have 1 plus. So now let me look at my x to the third. Oh, I have an x. Shoo, thank goodness. I have an x. Do I have any other x's in there? I just saw that. X. X squares cancel. Next thing is going to be x to the third. So I have an x to the third here. I've got an x to the third here. Nothing else has it. Are they just going to cancel out to give me 0? No, why not? Denominators are different. So I know it's going to be plus, but this is where I said you don't have to worry about getting common denominators and adding them together. It's okay just to write a negative x to the third over 2 factorial plus x to the third over 3 factorial. But you do need to group and show that it is a like term. That counts as one term because I do know that I could combine them. But in terms of free response, you don't need to combine them. All right, so any questions on that one? So now after x to the thirds comes my x to the fourth. I'm running out of colors here. Purple. X to the fourth. So here's my x to the fourth over 4 factorial. Here's a minus x to the fourth over 2 times 2 factorial. There's that other x to the fourth plus 4 factorial. So again, I'm going to add this, and I can group those 3 terms together. So I have an x to the fourth over 4 factorial minus x to the fourth over 2 factorial, 2 factorial, plus x to the fourth over 4 factorial. So there's my first 4 non-zero terms. Yes, I know that those first 2 terms at x to the fourth over 4 factorial. Again, remember, this is not 4 factorial right here. This is just the 4, so they're not going to cancel out. All right? So any questions on, yes, the multiplication can get ugly. They typically won't make you go more than 3 or 4 terms because they do get to be pretty ugly. All right? So again, I think, I've never tried, I just thought of that. Those of you who used those box methods before to do those trinomials, that may be another strategy to use when you're having to multiply them together. All right? So any questions on how you can multiply Maclaurin series together? So another operation you can do is, now notice these are only asking me for the first 2 non-zero terms. Don't get too excited. That means it's probably not going to be pretty either. If they're only asking you for 2 terms, that means there's probably a glitch to this. So cosecant of x, going back to my trig, cosecant is the reciprocal function of what? Sine. So now what I want to do, there is no Maclaurin that I know for cosecant of x. But I do know it for its reciprocal function sine, so I can change cosecant of x into 1 over sine x. So what you're going to have to do with these is long division. When you end up with a Maclaurin series in the denominator, you are going to have to use your long division. So now remember, I know that my Maclaurin series for sine x, so cosecant of x, is going to be equal to 1 divided by. And I know the Maclaurin series for sine is x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial. And that's where I'm going to stop. If you want to come into my pre-calc class, we're reviewing long division right now. So you're more than welcome to come in and review long division. They were very excited to hit long division today, too. So now what I'm going to do is I'm going to take x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial. And again, I'm going to divide it into 1. So now what I'm going to do, remember the way long division works, it doesn't matter how ugly it is, you always work with the first term. You're going to take the first term, divide it into the first term underneath of the division symbol. So I'm going to take 1 and divide it by x. I can't simplify that, so that is your first term of this particular Maclaurin. So now remember what happens with long division. You're going to multiply 1 over x times x. What is 1 over x times x? 1. 1 over x times negative x to the third over 3 factorial. Well, all that's going to do is what? Drop it down a what? Degree. So it's going to become a minus x squared over 3 factorial. Again, 1 over x times x to the fifth over 5 factorial. It's just going to drop it down a degree. And then 1 over x minus x of it is going to be minus x to the 6 over 7 factorial. What happens with long division after you multiply? What's the next operation? Subtract. So it's going to be minus. This becomes a plus. This becomes a minus. This becomes a plus. So the 1s are going to cancel. So next I'm going to bring down that x squared over 3 factorial. And remember, after you bring down, this is where you repeat the long division process again. So what I'm going to do is I'm going to have to take x, and I'm going to have to divide it into x squared over 3 factorial. So I have to take x squared over 3 factorial, and I'm going to divide it by x, which means I'm going to multiply by the reciprocal. So what's the next term then going to be for this particular Maclaurin series? It's going to be what? X over 3 factorial. And luckily they're only asking me for the first 2 terms, so I can stop. So there is your Maclaurin series for cosecant of x. So it's 1 over x plus x over 3 factorial. I wish it was easy that you could just say, oh, I'm just going to take the reciprocal of each individual term. No, doesn't work that way, guys. All right, so you do have to provide that long division. All right, so any questions on producing? So now you know how to produce your Maclaurin series for all the other reciprocal functions. You could do it for cosecant, you could do it for secant, and you could do it for cotangent. All right, you have to do the long division. Any questions on that one? Let's see. This is another wow moment. I just think this is really neat too. So we know, going into limits, we know with limits, if you end up with the indeterminate form of 0 over 0 or infinity over infinity, you have L'Hopital's rule that you can use to help you establish what a limit is when you have the indeterminate form. You can also expand your functions into Taylor series and taking the limit of the series if you end up with that indeterminate form. And then we can check this by using L'Hopital's rule to see how that works. So again, limit as x goes to 0, sine of x divided by 2x. Again, I can rewrite this as the limit as x goes to 0 of 1 over 2x times sine of x. Do you agree with that those are equivalent? You agree with that? So then what I can do is I can then take the limit as x goes to 0, and again, what I can do is I can take 1 over 2x, and I can multiply it by the Maclaurin series for sine of x. So I know my Maclaurin series for sine of x, remember, is going to start with x, minus x to the third over 3 factorial, plus x to the fifth over 5 factorial, minus x to the seventh over 7 factorial, and so on. Well, what happens when I distribute this 1 over 2x and multiply it by x? What happens with those x's right there? They cancel out. So I have the limit as x goes to 0 of 1/2 minus, and again, if I distribute this is going to be a minus x squared over 2 times 3 factorial, and I can stop. Because what happens now when I go to do the limits? All the rest of the terms are going to have what variable in them? They're all going to go to what? 0. So this is going to go to 0 because I'm going to plug 0 in for x here. I'll plug 0 in for x here, and so on. So what's the only term that's going to end up remaining? 1/2. Isn't that an aha moment? Isn't that neat? Come on now. Yes, you could have done this through L'Hopital's rule. Again, to check this, again, we know that if you did this by L'Hopital's rule, the limit is x goes to 0, sine x over 2x. When I plug 0 in for sine, sine is 0, 0 over 0. I get the indeterminate form. So then I can take the derivative of sine, which is cosine, take the derivative of 2x, which is 2. And then the cosine of 0 is 1, so there's also how you get the 1/2. But you can also use Maclaurin series for limits as well. See if you can do your Maclaurin series and figure out what the limit for b is going to be, and then check it. Don't cheat. Check it with L'Hopital's rule after you get done using the Maclaurin.